So hello and welcome to our 13th lecture on reinforcement learning, and in this video series we will talk about offline reinforcement learning. So what will be our agenda for the upcoming videos? So in the beginning I will talk a little bit about what is the actual offline reinforcement learning problem and why are we actually doing that. Then we will talk about challenges of offline reinforcement learning. It is not so easy to apply offline RL just as it is, and you will see why this is problematic in practice. And then we will talk a little bit about possible solution approaches, and there is basically two different kinds of solutions to the problem. The first methods are policy constraint methods that constrain the resulting policies to the policy that is part of that data we are learning from, and conservative methods where we try to get a conservative lower bounded estimate of the Q function. And in the end we will make a short summary on that. Okay, so let's talk a little bit about the general motivation of offline RL. And the thing that might be coming to your head, the question is, why is deep learning so successful in real-world applications? And the thing is that usually you see frameworks or applications like this. So you have a combination of large and diverse data sets, and you have high capacity neural network models or transformers or convolutional neural networks, things like that. And then you get actually a very good performance out of it. So in this example, you get maybe as an input an image or a video stream from within a car, and you process the data using a convolutional neural network, and you get, for instance, an image segmentation of this image, and you get a segmentation of all the elements that are within your environment. And the question is, why does this not really work in RL? So why is this not the same for reinforcement learning? And the problem is that in RL we're usually doing something like an active data collection. So an active data collection that we have an agent, and the agent interacts with the environment. It's a fundamentally different setting. In deep learning, usually you have a bunch of data and you have the data available in a database, and you can just sample from the data to learn your model. And in RL, we have an active learning procedure. So we actively collect experience and update our model. A value function, a policy, a reward model, or something like that. And then we iteratively start over again and collect new data. And an active data collection, usually in many applications, is not that easy. So this is the general RL setting. But we, on the other hand, have such applications such as medical treatment, where in general RL could be really beneficial. However, this active learning procedure might be a little bit complicated in applications such as medical treatment, because this might also hurt actual people. And in autonomous driving, it's like the same. So in order to have this active exploration of your agent, you might lead your agent, or you might lead your involved humans into dangerous situations. And this is also problematic because this hinders the application of active reinforcement learning to real-world problems that we can actually address in practice. And this is why we usually see simulators, and simulators are hard to design, and the resulting observations are usually inferior to real-world data. So there is a need, or there's at least at least we want actually have data-driven reinforcement learning that uses data that's already there. So you could imagine, for instance, that you have many recordings of an autonomous car, or even a non-autonomous car that drives through cities, and you actually want to use RL on that data set. And this is not easy with the methods we have seen so far. So still we want actually to have the data, and using this data we want to generalize well to new data sets. And exactly, so this kind of problems we usually have in RL. So we have closed world problems. They are usually much different than supervised learning methods, which are usually open world problems, and this is really problematic. And it hinders the application of a widespread application of RL in practice. So this is why we usually want to use something like an offline RL method to actually train an agent from offline data. I have talked a lot about offline data. What would we actually mean by that? So Usually what we have seen so far, or what we have seen in the beginning of the lecture, is the classical online on-policy reinforcement learning. So we have seen a lot of times this kind of figure. So we have a policy, and the policy interacts with the real world using an agent, and we collect new states and rewards, and we execute actions, and we use that rollout data basically to update our policy, and then we plug that new policy in and collect new data. So this is somehow like the textbook version of reinforcement learning, and you see exactly this online fashion active learning procedure in here. And usually what it means is that pi k and k are somehow the iterations of the updates of our policy is updated with the streaming data that is collected by pi k itself. And the transitions are usually collected using the latest version of the policy, and the policy and the transitions are then somehow perfectly related. So the transitions that we observe using our policy are actually the things that our policy collects. So this is somehow the textbook version of on-policy online reinforcement learning. Now, we also talked a little bit about off-policy reinforcement learning, or not a little bit, quite a bit. And it's not that fundamentally different, only a little bit. So we still have these k iterations where we update our policy and actually capture new data. However, we introduce a buffer. So meaning that essentially that we get new transitions using our current policy, and we append these transitions to the buffer. And using this buffer in the end actually consists of samples that we collected under very, very different policies. So we keep on updating our policies, and all the data that all these policies are actually generating are put into our buffer. And this actually means that the buffer is actually consisting of transitions that have been collected under different policies. And however, we use all the data from our current buffer to train an updated new version of our policy pi k plus 1. So the new iteration and the new policy resulting from it is actually trained from a bunch of data that's coming from a bunch of different transitions, policies. And this actually means that still the policy and the transitions are somehow depending. So there's ways of actually also doing importance sampling, but they are not so perfectly correlated anymore. They are somehow dependent, and the strength of this dependence actually depends on the size of the data and on our epsilons or our epsilon greedy strategies. So this is somehow the off-policy reinforcement learning setting. So we're updating our policy using data from different policies, but they are somehow a little bit dependent. And then there is what we want to talk about in this lecture. This is the offline RL setting. So in the offline RL setting, this somehow really changes. So you have some policy or a bunch of different policies, and those policies are actually interacting with the environment, and they are actually generating transitions from this environment. And you take all the transitions into a buffer, and then you have a training phase. And in this training phase, you actually do not interact with the real world, or you do not interact with the real world. You just have your buffer, and you train your policy on that buffer of data. And if you're done with training, you actually deploy the agent into the environment, and then you actually evaluate the agent. So there's no retraining then in the deployment phase of your agent. So this basically means that in offline RL, we use a data set D that is collected by some behavior policy pi beta, or a bunch of different trajectories, a bunch of different policies pi beta. And usually also what we're assuming in offline RL is that pi beta is potentially or often unknown. So we don't have the neural network actually that is implementing pi beta. And so the data set is collected once and not changed during training, so it's just there. And we sample the transitions from that buffer just like we do in supervised learning, and there's no interaction with the MDP, and we deploy the agent afterwards. So in this sense, the policy that we are currently learning and the transitions that we are learning from, they are completely independent. So there's no real interaction between those two parts. And if we have a setting like this, we could really in principle or theoretically assume that we have ImageNet style datasets in here. So we have really data coming from a diverse set of policies. Like if you assume autonomous driving applications, you could have transitions from different cities, so Berlin, London, Shanghai, things like that. And you can also have data coming from different policies, so conservative drivers, aggressive drivers, bus drivers, car drivers, motorcycles, and things like that. So you could really build kind of really large, diverse data sets that you could somehow use something like as a benchmark with an image set, like within similar to ImageNet, where you can really use high capacity models to actually come up with state-of-the-art policies to actually solve such environments. And this is the one side, and the other side is that you now could also, like theoretically, if this would work, you could also like apply it in critical use cases. So there's a lot of, like if you consider the medical treatment use case, there's a lot of records how patients actually reacted to certain doses or certain treatments, and you could actually use that transitions to learn a new policy from that without having an active interaction with an agent and try in order to try out some medicine on them. And you could also resort to different control transitions from power plants, where you actually control battery charging levels and renewable energies and things like that. And also in finance. So you could also resort to many data sets that are already out there without posing too much harm to the actual system. And you can just train the agent like offline using a supervised learning, similar to a supervised learning setting, and then evaluate your agent and put it into the real world. Okay, so we didn't really talk much about things like behavioral cloning in this class. However, you might actually have came through it if you have studied a little bit aside. So in behavioral cloning, so what's actually how's actually behavioral cloning related to offline RL? And in behavioral cloning, you usually have a scenario that looks like this. So you have a data, and data is collected from some behavioral policy or behavioral agent pi beta, and the goal that you actually have is to learn a policy pi beta from this, to learn the policy pi beta from the data set that you have with supervised learning. That is actually something that you see a lot in practice. There's a famous algorithm called Dagger, and using this Dagger approach, you can usually use it. You can actually resort to a data set and extract a policy from the data set. So you somehow try to create a policy that imitates the behavior that you see in the transitions that are in your buffer. This actually works also pretty well. However, if you have an application like that, you actually, and if you want to deploy a policy using a behavioral cloning strategy, you usually need to have expert data in that data set. So if you don't have expert data in the data set, you usually don't get a good policy out of it. So you first need expert data in there, and usually if you have a setting like where you then deploy the agent in a slightly different scenario, you usually have an unexpectedly high error bound because you have your agent does not really generalize well to out of distribution situations that the behavioral agent doesn't really see, or that you don't really see in the data. And this usually means that you have usually a poor performance when you deploy behavioral cloning agents into a new environment. In contrast to that, in offline reinforcement learning, we have a scenario that's a bit similar. So we have still data D that is collected from a behavioral agent, pi beta. And the goal is not to actually to imitate the agent that actually has collected the data. You actually want to learn the best policy pi using the data that you have in your data set. And we will see actually nice examples where you have where you actually see why this makes it fundamentally different in practice. So you might actually see data, like you will see a lot, like such corridor example. A corridor example is something that is like, in my opinion, very intuitive. So you have, imagine that, maybe I go spoil into the next video. So imagine situations just like this. So you have in your data set, your policy is actually went from A to B and from B to C. So in your data, you never really encounter a trajectory that goes from A to C. However, if you're tasked to go from A to C, a behavioral cloning agent will actually always go over B and then go to C. If you do offline RL, you're actually really uncover the actions that are necessary to directly go from A to C. Because you actually do not have that transitions in your data set. However, the agent uncovers the underlying structure of the reward function and the queue function that actually lets him approach C directly from A. So this is the fundamental difference, meaning that in a more broader sense that in order to come up with such a strategy, you do not necessarily need expert data. So you need like data that is representative, maybe not so bad at all, but you could like really come up with an optimal policy using only medium well rollouts of different agents, for instance, and then you can actually use this data to uncover perfect trajectories and hence also a perfect strategy to actually solve environments. So this is it for the motivation. In the upcoming videos, we will talk actually what are the challenges if we would just apply the methods we have seen so far to solve offline reinforcement learning, the offline reinforcement learning task on a static data set.